All right, so we are going to talk about, as the title suggests, extrema on an interval. And extrema, that's just basically your max and mins. And so there's some mathematical jargon. First, if I sent this out in OneNote under notes, so you don't have to, if you want to look along, you can. So as far as, this is like your mathematical notation. It says you have an absolute max if the y value is bigger than everything else, bigger than or equal to. You have a minimum if it's less than or equal to, the y values are less than or equal to. The problem is mathematical definitions don't make a bit of sense without a picture. So, we are going to look at, a picture, which is why I had this. Okay. So as far as absolute max and absolute min, you think, well, there's your absolute max, ta-da, right? And looks like your absolute min is here, right? So your absolute max or min can be anywhere in a certain range. Sometimes it's in the middle, sometimes it's at an endpoint. This is not an absolute minimum, right? And this is not an absolute minimum, this is not an absolute max, but anytime we talk about absolute max and min, we're just looking at what's the highest or lowest part of the function, right? And it's very easy to see when you have a picture. You just go, well, there, right? There's nothing to it, right? The trick is, what do you do when you don't have a picture, right? Like, how do you find the absolute max and absolute min if I give you a function, right? Well, one thing you could do is make a picture, right? I mean, you could just draw the thing, right? And this is simple enough we can draw, so we'll talk about it. But eventually you're going to work up to how do we find the absolute max and absolute min without having to draw the whole thing, right? And that's the goal. But there are a couple of little weird things that we need to talk about. So one little weird, so this, everything's normal, and like we know what this graph looks like. You know, this is a parabola, it's shifted up 1, and we're going from -1 to 2. And so at -1, we're at, so this is the coordinate -1, 2. And this is the coordinate 2, 5. And, you know, here's our picture. And if this is our picture, and I know, well, determine the extrema that exists, you know, what's our absolute max and absolute min? Oh, sorry, that's a 1. What's your absolute maximum value?
Infinity?
Yeah, 5.
Oh, 5.
Right, everybody okay? What's your biggest y value, right? And in case you haven't, I don't know if another teacher's talked about this, but code words in math are, usually whenever they say what, that means they're referring to your y values. And if they say when or where, that's referring to x values. Just in general, any math class. Right? So if I'm asking you, like, you know, what determine the extrema, like what's your maximum? So here, our maximum value, our absolute max is 5, and our minimum value, what's our absolute minimum value? Minimum y value?
1.
1, right? That's everything. Everybody okay with that? This is everything's normal. Okay. But now things get a little weird, right? So the difference between this and this is, okay, this includes, means I get to fill in the dots. And this open parentheses means it's not included, so it's the same picture, but now my picture looks like this, right? I'm still drawing my parabola, right? So here's -1, here's 2, right? But instead of, so I want to know what's my max, I don't want to know what's my min. All right, let's answer the easy one first. What's your minimum value?
1.
It's still 1, right? Not a big deal. Now here's the part that's kind of tricky. What's your maximum value?
Less than 5.
You got to give me a number.
4.9 repeating.
That's the same thing as 5. That's the tricky part, right? Does everybody see there's an issue, right? If you're going to give me a maximum value, you have to, if I want the maximum, you have to give me a maximum value. And can you give me a maximum value? And since you can't give me a maximum value, there is no max. Kind of counterintuitive, right?
Yeah.
See, most things you think max means it just goes off to infinity. And there you say, well, there's no maximum because it goes off to infinity. And you'd be right. That's true, right? But this is kind of those weird cases where if you can't give me the number, you can't. If I say, what is your maximum value? You can't give it to me, it doesn't have a maximum. All right, so sometimes you don't have a maximum when this is clearly bounded, right? It doesn't go off to infinity, right? But since you can't give me a number, you can't set maximum. And this last one, all right, all this is really saying you still have the same parabola, right? We still have our same parabola. Here's -1, here's 2, and here's, I get a dot here, but now I get a circle, and then I get a dot up here, and then I fill this in. And, oh, whoops, the both gets filled in. So your max, in this case, is 5, because we can tell me the dot, right? But what's your minimum value?
Doesn't exist.
None, right? Because you can't tell me, right? Because it doesn't include. That's our counterintuitive stuff. Let's see. Let's look at the rest of these. This one's boring. This one's kind of interesting because it's just one of these weird cases. Like for this one, like what's the max and the min of the sine graph from 0 to 4 pi? I mean, if you think about the graph of sine, let's see. Oh, wait, am I doing this right? Yeah. Oh, I can't draw, but like what's your maximum value of sine? 1. What's the minimum value? -1, right? So that's pretty easy. Now, okay, we got a line, right? So let's see if we can figure this out without drawing the picture. Right? Well, since you have a line, can we, and we're including the endpoints, can we agree that the max or min are going to be at the end of the lines?
Yeah.
Right? So what I could do is I could say, well, what's f of -1? Well, f of -1 is going to give me a 5. And I say, what's f of 2? Yeah, so 2 minus 6 is going to give me -1. Right?
2 minus 6 is -4.
2 minus 6 is -4. Thank you. That arithmetic stuff's tough, but right now. So based on this, since I plugged in my endpoints, we have a max of 5 and a min of -4. And since it's a line, are we guaranteed those are going to be a max and a min? Yeah. Now, if that was a parabola, you don't know, do you? Because a parabola could do something in between. But since I know this is a line, right? In fact, I mean, it's a slope of -1, right? So, I mean, slope of -3. My max is going to happen at the first spot, and my min is going to happen down here. And this one's kind of weird. What's your maximum value? Well, if I were to graph this, this is y equals 3. That's just a horizontal line, right? What's your maximum value?
3.
3. What's your minimum value?
3.
So this is one of these like weird cases where your absolute max and absolute min are the same number, based off their definition. But no one really asked about that. Oh, well, there you go. Under what conditions do you think have both an absolute max and an? All right. So now we get to start using some calculus terms. So we have something that's called the extreme value theorem, which is a whole lot of syllables. It says, if your function's nice, meaning it's actually not even super nice, it's just continuous, right? And it includes the endpoints, you are guaranteed to have a max or a min. You're guaranteed to have a max and a min. If you don't believe me, try to draw something. Yes?
Sorry, what were the max and mins on the straight line? Were
The
they
same.
both 3? Okay.
They were both 3. Okay. So your extreme value theorem, which is like, why is this even a theorem? It says, if the function's continuous, all right, meaning, here's the challenge. I want you to draw something that's continuous, right, that doesn't have a max and a min, right? So we might think, well, wait, can't I just do what you did before, right, where I do these, like I do this open circle and this open circle, right? This doesn't have a max or a min, but I said that over the closed interval, meaning you have to include the endpoints. And if you have to include the endpoints, do you see that you're guaranteed to have a max and a min? It doesn't matter what goes on in between, right? You can start here, you can start here, you can do all sorts of weird stuff, right?
Yeah.
But you're still going to have a max and a min. Right? Which seems kind of, now, here's the crazy part. Does that seem obvious?
Yeah.
It's like, why is that such a big deal? Okay. Proving that is a royal pain. I mean, it gets into limits. I mean, it's this long, right? You don't have to do it in high school, but if you take something called real analysis, you have to. And it's a pain to prove that, right? So what seems absolutely obvious, like, well, duh, just draw it, right? To explain it mathematically is not so easy, right? So let's see, some pictures. Oh, here, we're drawing some pictures. All right, does it have an absolute max? Yep, there's your max, there's your min. Does it have an absolute max? Yep, there's your max, there's your min. Got a max and min. Notice our max and min are in the middle somewhere. Here, the max is here, the min is on an endpoint. And again, here we have a case where you have the maximums are at the same height. But when you're looking for a max or a min, that's maximum or minimum y value. So it doesn't matter that it repeats twice. Okay. So let's talk about why we don't have it. Does this follow? Is this continuous? No, it's not continuous, right? The endpoints are included, which is great, right? Because there are two things that have to happen for you to have an extreme value. It's got to be you've got to include the endpoints, but it also has to be continuous. So here's a case where, all right, the endpoints are included, but because it's not continuous, does it have a maximum? No. It happens to have a minimum, but extreme value, the extreme value theorem doesn't work here. Does the extreme value theorem work here?
No, because there's no given endpoint.
Well, I don't have either endpoint, right? And since I don't have either endpoint, it doesn't work. The extreme value doesn't work. Does the extreme value theorem hold here? Or is it continuous? No. Do we happen to have a maximum and happen to have a minimum? Right? But the extreme value theorem doesn't work because this isn't continuous, right? Same thing over here. I happen to have a maximum and I happen to have a minimum, but the extreme value theorem kind of requires that it includes the endpoint. So it doesn't have to have all the parts to have a max or a min. The extreme value theorem says if these two things happen, then you're guaranteed. But you can't have it without the guarantee. And we've already talked about that one. So I guess I should talk a little bit about calculus because it is a calculus course, right? Because I haven't really talked about calculus at all, have I?
No, not yet.
Right? Because calculus means I'm probably going to talk about a derivative, okay? So what do we do? Well, so most of this, basically what I've talked about so far is here I've given you a nice little picture, and how do we find things, right? How do we find the absolute max and absolute min given a picture? Well, it's very obvious. Just look at it. But what if you don't have a picture, right? What if, here, let me see, I've got wait for me. And actually, I'm going to talk about that in just a second. So before I talk about the calculus part, I want to talk about local, relative or local minimums. So I want to go back to this picture, because to talk about that I need to. So we're going to talk about local max and local mins, right? So absolute max and absolute min is simply what's the highest and lowest point. Local max and local mins, there's a little better, there's a more precise definition of that. And I'm going to paraphrase it just because I like a working knowledge as opposed to like the whole mathematical thing. So if I want to talk about local max, that means it has to be bigger than the points around it. This is an example of a local max. See how it's bigger than the points around it. This is an example of a local max. See how it's bigger than the points around it. Right? Here's an example of a local min. Here's another example of a local min. See how you've got like a peak or a valley? Back when we first looked at this picture, I said this was an absolute minimum because it was the lowest point. This is not a local minimum. For something to be local, it has to be lower than the points around it, meaning it has to have points to the left and right of it. Are there points to the left and right of this? No. So this is not, endpoints can't be local maxes or mins. All right? And what I need, and that's just some ugly example he came up with. So I want to minimize this. Need a different example. So let's say I give you y is equal to x squared minus 3x plus 2. Right? And I'm going to say I'm interested in the interval from 0 to 4. And I want to know what's my absolute max and absolute min. Now, one obvious way I could do this is I could just draw the picture, right? It's a parabola, right? We could graph it. But I don't want to graph it, right? What I want is I want to find my absolute max and my absolute min, all right? Could the absolute max and absolute min occur at the endpoints?
Yeah, they could.
They could, right? Right? So what I'm going to do is I'm going to make a little xy chart, and I'm going to plug in 0, and I'm going to plug in 4. And I plug in 0, I get a 2. When I plug in 4, let's see, 16 minus 12 plus 2, so 4 plus 6. Okay. So based on this information, what does it look like your absolute maximum value is? And what does it look like your absolute minimum value is? 2. Do you think those are the absolute max and absolute min?
No.
Yeah. At least for the minimum. Okay.
Well, do we know what's going on? Like, here's a picture of what's going on, right? A picture of what's going on is at 0, we're at 4, right? And at 2, or sorry,
4.
at 0, we're at 2. And then at 4, we're at 6, right? Do we know what's going on in between here and here?
No.
No. I'm fairly certain it's not a straight line, right? Can everybody agree on that? Right? So, we know it's a parabola, right? Does the parabola do this? Does the parabola do this? Does the parabola like way over here and it do this, right? See, if the parabola is way over here and it does this, then this is a min and this is a max and we're fine, right? But what if the little dip is here, right? Is everybody kind of at that one spot where, does everybody understand that we don't know exactly what's going on in between here without graphing?
Right, yeah.
Okay, so how do we find out what's happening without graphing the whole thing? Right? You could, well, that's essentially graphing the whole thing, right? Like if we're back in pre-cal or algebra 2, we could graph it on a calculator or plot a whole bunch of points to simulate graphing on the calculator. But my goal is, like this is a real simple example. They get much harder, right? Much more complicated. How do we find out what's going on without, plotting an obscene number of points, right? So let's think about a graph for just a second. So I'm going to draw a picture. Right? Here's my little picture. Yay. Right? What's special? There's a local, everybody okay, that's a local max.
Yeah.
Oh.
What's special about that's using calculus?
The derivative is 0?
The derivative is 0. Does that make sense? Right? Because any time if
Oh, it's horizontal.
you get a horizontal tangent line, like for you to get a peak or a valley, can everybody agree that your derivative has to be 0?
Yeah.
So what that means is everywhere that your derivative is 0, that's a place where you could have a peak or a valley. Right? So what I could do in my little example is I'm going to look at my derivative. Okay, so y prime is equal to 2x minus 3. And when I set that equal to 0, right? What I want is I want to know where is my derivative 0. Where is my derivative 0? So I plug that in. That's going to give me, that's going to give me x is equal to 3 over 2. Right? And so here's what that's telling me. First, how many places is the derivative equal to 0 in this problem? We took the derivative, right? We solved. How many answers did we get?
Oh, just 1.
We just got 1. So there's only one place where the derivative is 0, right? And if your derivative is 0, that means that's where you could, it's either going to be a valley or it's going to be a peak.
Oh, and that's in between the points you plotted.
Yeah.
See
So,
how it looks like that.
Well, I don't know. I've got to plot the point, and I should have. This is what happens when I make numbers off the top of my head. Now I get the joy of computing that. Yay! What's that? 9 over 4, and minus 9 over 2 plus 2, 13, minus 9 over 4. Oh, minus 1/4. Okay? And so here's what I know. What I know is at 3 over 2, I'm at negative 1/4.
So it looks like that.
And so we can kind of look at this and say, oh. Now, based on this information, what's our absolute max?
Oh,
6.
6.
Okay? Right? In this interval, right? Is everybody okay? Our absolute max is 6 in that interval, right?
Yeah.
What's our absolute min?
Negative 1/4.
Negative 1/4, because we're looking for a y value. All right, now here's a better question. All right, how do I know there aren't any more?
Oh, you don't, because we,
No, you do.
the interval
Okay.
isn't
No. How do you know there are not any more in between 0 and 4? And here's how you know these are the only ones. For me to get another peak or a valley, the graph would have to turn, wouldn't it? The only way you get peaks or valleys is if the graph turns, right? What happens to your derivative when the graph turns? Becomes 0, right?
And there's only one.
And there's only one place where the derivative is 0. So this is your only turning point. And since this is your only turning point, right? Then so what we know is we've checked our endpoints and we've checked the only turning point. And once we have that, then we have enough information to say, I know what my absolute max and absolute min. Now, personally, my first few years teaching, I did not stress this. I always stress taking derivative set equal to 0. You got to. That's pretty much the rest of this chapter. But what I didn't stress is checking endpoints. And there's a problem with not checking endpoints. Whenever you're asked to find the absolute max or absolute min, you always check the endpoints because your absolute max or absolute min could happen there, right? Now, in college, I'll go ahead and tell you most of the time it doesn't. On the AP exam, on free response questions, it does. So anytime you're asked for an absolute max or an absolute min and you don't check your endpoints, you lose a point. So rather than fix this when you're getting ready for the AP exam, and I'll keep repeating it then, because what we're looking for today, and actually throughout the rest of this chapter, we're going to be looking for absolute max and absolute min. You always check your endpoints. Because sometimes what you're looking for happens at the endpoint. 80% of the time, what you're looking for happens somewhere in the middle. Right? But on the free response question, if you don't check your endpoints, you lose a point. And I hate to lose an easy point, because how easy is it to check the endpoints? I mean, that's the part that doesn't even require calculus. And I'd hate to lose a point. I'd hate for you to lose a point for, an Algebra 2 concept. Okay, so these turning points are kind of important, aren't they?
Yeah.
Because they determine, right? They determine, for the most part, they're actually going to determine our max and mins and what we're looking for. They're so important, they're critical. And that's what they're called. They're called critical points. Right? And how do you find critical points? Critical points are places, there's two conditions. And I'll bring up the little menu. Critical points are, get back to the definition. Where is this? Okay. Critical value is a place where the derivative is 0 or the derivative doesn't exist. Okay, let's look back at this picture. If we are looking for local max and local mins, that's a local max, right? You see our derivative is 0? That's a local max. See our derivative is 0? That's a local min. You see our derivative is 0? This is a local min. What's our derivative? Doesn't exist because it's a cusp. All right. So
what happens then?
no, it's still. I mean, here. I'll go through some examples here.
Oh, okay.
So now, this idea of a critical value, right? All right. What's a critical value? A critical value, as they've defined, is, so a critical value C is where f prime of C is equal to 0, or f prime of C is undefined, or does not exist. All right, so we're going to look for things, right? I want to find all of my critical values, my x values. And how I do that is I take the derivative and set it equal to 0. I want to find out where is my derivative 0. So I take the derivative of this, so it's going to give me 2x cubed minus 3x squared minus 2x. Yeah, I'm going to factor out an x, and so I get 2x squared minus 3x minus 2. Let's see, I think that's 2x and x, and it's going to give me minus 2, yeah, no, plus 1. Yeah, minus 4 plus 1 gives me negative 3. And so in this problem, I get critical values at x equals 0, negative 1/2, and 2. And what that's telling me is at 0, I get a flat spot. At negative 1/2, I get a flat spot. And at 2, I get a flat spot. Right? And those are places where I could have max or min. I could have max and min. As far as taking a derivative of absolute value, there's ways to do it. I don't like it. We're just going to skip that one. The mathematics, you got to do piecewise function. It's a royal pain. This is interesting. And this is calculus is actually the first time that you encounter a function that looks like this. And what I'm going to do is I'm going to do the calculus, and then I actually want you to see what that picture looks like. So I'll pull up a picture of it. Because when we do the work on calculus, you go, what? Right? Because I'm going to talk about it, then I want to connect a picture to the calculus part. All right, so how do we take the derivative?
Product rule.
Everybody okay with product rule? And so when I do product rule, that's going to give me, what's that, 3/5 x to the negative 2/5 times 4 minus x plus derivative of that, which is just going to be a negative 1, times x to the 3/5. Well, that looks absolutely miserable. Let me clean it up. So when I clean this up, that's going to give me 3 times 4 minus x over 5 times x to the 2/5 minus x to the 3/5 over 1. I'm going to get a common denominator, so I'll multiply this one top and bottom by x to the 2/5. I'm out of room. So I get 3, 4 minus x all over. It's going to give me 5 times x to the 2/5. That's 12 minus 3x minus x. So I end up with 12 minus 4x all over 5x to the 2/5. Don't worry. Are you going to have to do stuff like that? Yes, not so much today. That's more fun and excitement in the future, but I'm not going to worry about that today. What I do want to talk about is information that we found out. Like, what does this tell us? And so, what does it tell us? Here's our derivative. So I have f prime of x is equal to 12 minus 4x over 5x to the 2/5. Is there a place where the derivative is 0? Can I set that equal to 0?
Yes.
Okay, if I set that equal to 0, what x value gives me a derivative of 0? When you set a fraction equal to 0, you set the top equal to 0. 3. Is everybody okay with that? Is everybody okay that 3? Right? And so when I set this equal to 0, I set the top equal to 0, I get a critical value at x is equal to 3. Is there a place where the derivative is undefined? Is there a place where you're dividing by 0? What happens when x is 0?
Oh, you divide by 0.
You're dividing by 0. Is there a derivative?
Yeah, 0.
Everybody see that? Okay, so we also get a critical value at x equals 0. So here's what we have. And I'm just going to write it. I need to write this down so we can look at it. So f of x is equal to x to the 3/5 times 4 minus x. And I know that f prime of 3 is equal to 0. And I know f prime of 0 doesn't exist. Everybody okay with that? So, first, is the function continuous? Are there any problems in the function? Are there any values of x that give me problems? Are you dividing by 0 anywhere?
Yes.
In the function?
Oh, no.
Am I dividing by 0 anywhere in the function? No. Am I taking the square root of a negative? I'm taking the 5th root of stuff, right? Can you take the 5th root of a negative? Are there any restrictions?
No.
I can plug any number I want into this, right?
Yeah.
Like, here's your two problems, right? You can't divide by 0 and you can't take the square root of a negative. That's it, right? I mean, there's some other things, but for the most part, and when we get logs or whatever, but for the most part, you can't divide by 0 and you can't take the square root of a negative, and we're not, right? So this is continuous everywhere, right? But before I graph this, I want to make sure we're talking about it. So at 3, when your derivative is 0, what does that tell us about the graph? When your derivative is 0, what does that tell us about the graph?
There's a maximum.
There's or a min, right? There's a flat spot. Is everybody okay? If it says if your derivative is 0, that tells you get a flat spot. What does it tell you when your derivative is undefined? So imagine a continuous function where the derivative doesn't exist. What does that look like?
It's the
A cusp thing.
angle.
Yeah, like an angle, right? So if I were to graph this, what we should see is a flat spot somewhere, right? And we should see a cusp, right? Because that's what the calculus is telling us, right? Right? If it's continuous, right? So let me pause.